Don't do this at home unless you're a trained professional like me. The fire hose rodeo, or just have Jackass movies on TV and elsewhere. That's what this is off, I think. You saw the disclaimer. So. Yeah, well, certainly on a hose you can do it, right? So if you're a fireman, you have to anchor yourself, and so yeah. So it's not so different actually from our previous view of, I guess, a bunch of other things on here. What else we got? This is kind of interesting as well.
The jet suit as.
So this is in the UK, I think it's in Wales. Mountain rescue, the idea to be able to get up a hill quickly, to be able to, is that me? No, it's not me. To be able to rescue people, which is kind of interesting, just with I guess it's just, I don't know if there's something in the back. I think the back is fuel, and maybe there's a jet coming out of the back, but certainly there's jets coming out of the arms, and there's one top and bottom on each wrist, to be able to direct it. Doesn't get you very high off the ground, but certainly gets you up that hill faster than you'd have made it if you were walking, for sure. So I think that's kind of an interesting application. What else do we got? Oh, I didn't want to. I wanted that one actually, because I knew what it was. Yeah, this is interesting, I thought. Well, it's kind of a bit military, but anyway, kind of curious. So exactly the same idea, but in this case, using a jetpack and using it to board a ship, I guess. So when they finally get going. It looks like it's almost exactly, it looks like little jet engines, right? With a filter in the top, and must be, I don't know if it's hot air coming out the bottom, because it must be burning something, obviously, to be able to do that. So I guess you're a bit vulnerable, not holding a rifle when you're going in there, if that's the need for it, but it's quite neat. I remember seeing these at a Bastille Day celebration in France of a French soldier standing on a platform that was levitated like this. So anyway, so interesting application again. Same ideas, a bit like our, what else did we look at before? Oh yeah, we looked at this before and we'll use this today. Jesse Sharp, I guess his name is. I think in 1990, because I remember I was going across the border at this time. Not this way, was going across the border. This looks like it's photographed from the Canadian side of the falls. And yeah, I remember specifically, our daughter was six weeks old, and I went to teach a short course up in Waterloo, and this was on the news, as I remember. So, not such a great idea. People do, as I said, go off the falls in barrels, but and maybe in kayaks for that height. I think I looked up the height. I think the height is 40 meters, and they did find his boat. He was a guy from Tennessee, as I recall. They found his boat, but not him, ever. And some of these other things we looked at already. So, fire hose, and then this one. So we'll do some of these today, look at them again, just for the heck of it. Actually, this is the same principle, really, isn't it, as the jets on your wrists kind of idea, but just a different configuration. It's obviously shooting water rather than air. And if you're shooting water, of course, you have to have a source of that water. So hence the umbilical and the sled that's being towed behind him, which is just a pump, I presume, to build it up to pressure. And so I guess the great thing about a jet engine is that the mass that it uses to accelerate you is available around you. It's just the air around you. And so you don't have to have a 35,000 foot umbilical attaching you to the ground, which obviously wouldn't be very, very practical. So quite interesting in terms of this. So that's kind of the things. We'll talk about some examples of those today. So that's our plan for today. So that's to whet your appetite. I don't know what this is. I don't want that. No, I don't want Canvas. I want this. Don't forget. So someone asked last time about the midterms, and about what you have to do with them. You should have received an email and you should have made an appointment, right, to do it sometime during the day on Monday. Did that email come on Monday morning? So I guess another one will come today for next Wednesday's midterm. Fridays is in wherever you want to do it, and it'll be online using Canvas, 30 minutes, 8 to 8:30. And so I apologize that we've juggled it this way. I did have a Pollock Testing Center thing on the 28th, but it seemed that it's kind of out of sequence, so I decided not to do that. And so we'll do it in this form. I'm pained that we have to do it this way. It's actually really inconvenient to do it, for me to do it through the tester. I know you don't care about that. I don't know whether it's inconvenient for you or more flexible for you to do it any time during the day for half an hour rather than do it on the Friday at 8 to 8:30. But I think for the testing center, so you should have booked an appointment. You need to turn up. I think you need to turn up early. If you arrive there more than 15 minutes late for your half-hour slot, I think they'll refuse you entry. I got an email yesterday, coincidentally, as generically sent, I guess, to all the instructors saying we've had lots of abuse hurled at the people who monitor the test center. I'm sure that won't be you, but I think it, yeah, not surprisingly. If people get there late and get barred from going in, perhaps they are kind of annoyed about it, because that cuts off that avenue. I presume you need to take ID. I presume you certainly need to take a calculator and a pencil. You can take scratch paper if you want, but I think they'll give you scratch paper. The irony of this is that, I'll get you, the irony of this is that I had to send over a ream of scratch paper. I thought that with all the tuition that you pay, they might be able to supply you with scratch paper, but I had to send it, yeah.
Will we still have class next week?
We could talk about that. I'm happy to kill it. Who wants to have class next week? You noticed why I asked the question. Who doesn't want to have class next week? All right, we'll kill it. So I need to decide. Yeah, I have my Friday midnight letter to, and I did have it crossed out. But yeah, we can get rid of it. That's fine. Surprisingly, some people complain about not having class and having tests instead. I remember in the SRTs last week that was a deal. So don't derail me. Make sure you bring ID, I presume. Pencil, calculator. There won't be one online. The one online that we can use on Canvas is just too rudimentary. So bring your own calculator. Scratch paper, you probably won't be allowed in with it, and they'll give you some. And the equation sheet is appended to the bottom of the exam script. The same equation sheet for each test on the 3 days, and it's just a screen capture of the equation sheet, which is in the review video. And of course, the review video, if you haven't found it yet, is on this. It's this. It's just this a screen capture of that equation sheet, and that's halfway through it, right? It starts off. It's just exactly that. So that's it. I noticed that 30-some of your number are not registered yet or haven't an appointment. So I'll send out an email to remind those who might not be here. I'll also speak into the screen. You need to make an appointment. And that's about it. So that's just a natural consequence of the way we do things. We have to have assessments because we don't have attendance. I'm really anti-attendance type things. I think having an assessment that allows you to show your prowess is great, and just having people show up because they have to tick a box, and not you, you're showing up because you want to, I hope. No one's dragging you here, but that's part and parcel of it. Okay? Any questions? Yeah.
So we don't have class next week, or are we just going to do the lectures?
Yeah, I'll put it up for extra credit. So that will boost by an extra percent, 1/3% each. So, hey, perhaps you want to cancel class the rest of the semester. I'm happy to come, but yeah, no. So next week, week 6, it is. So we'll finish with Bernoulli today. On Friday, 4 and 5. 6, 7, and 8 are conservation laws. Conservation of mass. Mass in equals mass out. Kind of the V1 A1 row equals V2 A2 row that we talked about last time. in a more sophisticated way. We have conservation of momentum, which is F equals ma, and which is really Bernoulli, but written in a much more general form. And then we have conservation of energy, which is actually the jet engines. It kind of where it gets into thermodynamics, where there's a connection between fluid mechanics and energy expended versus chemical energy, which you burn to be able to power something like these hover wristbands or whatever you call them. So that's our plan for the rest of for the next 3 weeks. So 6 will be conservation of mass. Okay. And today I was just going to go through some examples. We didn't get as far as we might have done last period, which was on Monday. So I thought we'd move on from there. And so to bring that back, where is it? Yeah, this. So the first example that we might try is just trying to characterize this. What do we need to know? So if you need to design this, I guess you need to know what kind of size power motor you need in the pack that you're dragging behind the umbilical to be able to lift a person. And we have enough information to be able to do that. It's actually not very different from the San Francisco International blowing a truck off the runway calculation. You have something with velocity squirting out of it, which is the orifice either side of your shoulders. And you have that impacting on the water below, which provides a reaction, pushes the truck off. Air going horizontally or water going vertically, it's really a very similar process. And so we'll try doing that. And depending on how, and if we're still game, maybe we'll do the Flying Scotsman, which is, I guess I can just make it larger, which is this guy in Argyll in Scotland, hence we talked about last time. And actually it's almost exactly the same as the jet engine, right? So we said that to use Bernoulli, we had to use steady state. There are 4 requirements: inviscid, incompressible, irrotational, and steady state. And of course, this isn't steady state if we're sitting here and the guy zooms past you, because originally the velocity at the front of this thing was 0, was being pushed upwards. And then once it's gone past, it all goes, as the eddies settle down, it goes to 0 velocity. But what we can do, bless you, is we can attach ourselves to this, just like sitting in a plane and looking at the wing, and imagine that the air is coming to hit this at a velocity, whatever he's going at, assuming he's static, and he's being hit by that velocity, and it makes its way around it. And so we can do a couple of examples that just explore that. So let's try that. So, yeah, the other thing. I guess I had another thing on my desktop which I wanted to look at. And it's this. Yeah, I guess it also relates to what we talked about last time. We'll use this many times, especially when we talk about conservation of mass in week 6 next week. This is my downstairs wine room, where I used to, in my days, used to make beer and wine, not so much now. So it's a sink with a little plinth over it, so you can put these big 5-gallon demijohns on it and 5-gallon food containers, or a pint glass, a 20-ounce pint glass, and a faucet. And you see exactly what we talked about last time. We talked about a free jet. So the velocity of a free jet was using Bernoulli and writing the pressure at some location at the top of a tank, 0 pressure, 0 velocity. We could write the velocity where it comes out using Bernoulli, and it comes out to being that the pressures everywhere are 0, but therefore the magnitude of the velocity is 2 times g times the height, the depth down. And so that means that the velocity here is lower than the velocity here, and therefore from continuity, the fact that the same volumetric flow rate of fluid has to be crossing a section which is here as is crossing here, this velocity is smaller, this velocity is larger, therefore this area has to be larger and this area smaller by definition. So as it comes down, it has to taper, and you see that exactly here. So you don't have to take my word for it. And so this is something that I just use for talking about conservation of mass, which we'll do next time. All right, so I digress. Let's do some examples. I guess I wrote this as we were going out last time because it is 5-2. This is continuity, which is this expression here. We've explained exactly what that is. Where's my thing? This is continuity. It merely says that between two streamlines, that the product of velocity and area and the product of velocity and area multiplied by density, if we think the density is going to change, has to be constant across those surfaces. And the reason for doing that is that it allows us, if we're trying to solve Bernoulli, where we haven't worried about these terms yet, don't care about these. If we're trying to solve Bernoulli between upstream and downstream with 6 components, we have one equation, so we need 5 knowns to solve for one unknown. If we have 2 unknowns, then we can write the velocities and link them to each other because they have to be linked. So we can link the 2 velocities to be able to solve the problem. So that's what we're attempting to do. So let's do a couple of examples. So I'm going to do I don't know how you prefer doing this. I could import some equations in here, but we could also just do it by hand. And I don't know whether you like drawing these things or not. This is our guy, or gal, was a guy in our particular one. And we can evaluate that by, I think, thinking of it like this. And well, let's use some colors. So well, it didn't change. Didn't change again, never mind. So we could think about this. So Bernoulli is constant along this streamline. So you could think of this, I suppose, as a streamline. I don't know why this won't turn on, but you could think of this as being a streamline that comes down through here. And so if you write Bernoulli, as I like to write it in terms of lengths, pressure divided by unit weight, another length, and velocity head, v squared over 2g. And then we could think about what we know. We certainly know what this is. We know this elevation. Our convention is to have z as positive upwards. We know that this would have some kind of weight attached to it, which is the mass of everything times g. Pressure, I guess we'd probably need to know. And velocity squared would be, if it's a big tank, then this would be approach 0, right? Point 2, velocity is high, squirting out of it. The elevation we know. The pressure we know, well, we have atmospheric pressure acting horizontally, so probably, since it acts equally in all directions, might be close to 0. This elevation here we would also know, and this one, right? And what would we know? We'd know the velocity here. The velocity would be high. It would be coming out of here at some velocity. It would be accelerating because it has gravity acting on it, like a free jet, and therefore it would be a narrower cone at the bottom. Pressure, I guess we could also say that this is atmospheric right here. And so we could think of this as almost 0. And then here we kill the velocity, we're destroying all the momentum. So this goes to 0, and this goes to being quite high. So that's kind of the system that we need to look at. And so if we wanted to look at it, we could, how are you going to do it? So I'm going to just look at it at this point here. I'm going to look at points 3 and 4. So what do we got? Z1 plus P1 over, sorry, not 1, just said 3. Let's do 3. P3 over gamma plus V3 squared over 2G equals Z4 plus P4 over the unit weight of the fluid. I should stop talking symbols and say what they are, times the velocity at 0.4 squared divided by twice the acceleration due to gravity. So what do we know? These are roughly the same location. I should number them. We could think about this being supported by some weight. We'd like to be able to know what the pressure is that's acting up on this surface here. So I'll just draw it as this. So this is P4, bless you, acting upwards, times area 4. It's the area of the jet, right? And so these are roughly the same as each other, I would say, because they're pretty close. They're not 0, but they could be 0, I guess, so they're close to 0. Pressure at 0.3, we said, should be 0. This should be a big number. Pressure at 0.4 should not be 0, but the velocity at 0.4 should be. So we just have these two components. A bit like a free jet, except now no, actually not like a free jet because there's no elevation involved. So it would be P4 times unit weight is equal to V3 squared over 2G. And so I guess we could rewrite that as P4 is equal to V squared over 2G times the unit weight of water, which is being squirted. So that's one expression. We know that that pressure, if we drew a free body around something, so if we drew a free body around this, which remember our concrete step, we talked about the free body we had to draw. So if our free body includes all of this, then we have a weight acting downwards, which is mg, which is equal to w. And we have a force acting upwards, which I'll call uppercase P, which is just P4 times A4. And so if we want to calculate what uppercase P is, it's going to be equal to, we can just multiply both sides by A times A. And this term here automatically is equal to P, uppercase P. And that has to also be equal to mg. So P is equal to mg, which is equal to this expression here, which should be V3 squared, unit weight of water, times A over 2G, which is equal to V3 squared rho G times A times 2G Is that what I get? Something like that. So if we wanted to, I guess, you could imagine that we want to solve it for the velocity of the jet that comes out of it, right? That would be a design parameter. So just rearranging that, we have v3 squared equals 2mg over density of water times the area of the jet, which is A4, which is also A3, by the way, which is so I put some numbers on here. Let's see what my numbers are. 2, mass of a person, 100 kilograms, which is 1,000 newtons. So 100 kilograms times 10 meters per second squared is 1,000 newtons. Divided by the density of water, which is 1,000 kilograms per meters cubed, times an area. I think I thought, I don't know what that jet is, but I think it's 4 inches. 4 inches happens to be conveniently 0.1 of a meter, so area squared is 10 to the minus 2 meters. 10 to the minus 2 meters squared. So, and I have my pace notes here. I think that's exactly what I have down. You can check the units to work out, and V2 ends up being, it's not V2, V3 ends up being 2 times 10 to the 2. I guess you can do that just by seeing this, right? And 2 times 10 to the 2, that means V3 is equal to square root 2, which is 1.4, times 10 to the 1. So, sounds reasonable. And a meter a second, 2 meters a second is about a mile per hour, or a mile per hour is 2 meters per second. So double that, and you get miles per hour of the jet. So that's not how fast he's going, but that's how fast the water has to come out of here. And I suppose the other thing that you can do with that, if you wanted to, is you can say that the power is equal to force times velocity, right? Force is in newtons. Velocity is in meters per second. So in terms of units, that's in Newton meters per second, which is a joule per second, which is equal to a watt. The rate of doing work. This is work, joules are work, watts are rates of doing work. And so if you take the force that's applied, so the force is to hold this person up, which is 1,000 newtons, times 14 meters a second equals 14 kilowatts. Yeah, that's it. Sounds about right. I don't know how much 14 kilowatts. I know that when we're looking at putting solar panels on our roof, our electricity bill, we use about 24 kilowatt hours per day. So about 1 kilowatt, really low electricity use in our house. So 14 kilowatts. Does anyone know the conversion to horsepower? I have no idea, but we could Google it, I guess. But that's so. So you know you can dimension what velocity you need. You know what power that is. If you had a perfect pump in your umbilical and there were no frictional losses along the umbilical, then this is exactly what you need. You'd need much more than this because you have to push against the resistance in the pump and the pressure losses going around the corners in the nozzles, etc. So that's that. So that's it. That's how to do these ones. Yeah, I did it for the Flying Scotsman. I don't know whether it's worthwhile doing that one again. If you want to do the Flying Scotsman, actually, why don't we just go here? So if you're wondering what's on the desk as I sit here, these little paste sheets that I have, they are, well, this is on, so there you go. Instead of me writing it down, this is what we just did. If you want to take a picture of that, that's exactly what we just did. Isn't that neat writing? God, fantastic. So the bottom one is the Flying Scotsman. And so I'll just walk through it, take a picture if you want. But the rationale is this. You have the guy in the cowling. It's got a front face to it. It's got an area to it. You know he's going at 60 miles an hour, which is about 30 meters a second from the conversion that we just did. We can do Bernoulli again. This is just Bernoulli written at this particular point here and relative to a point here, because this is a streamline that comes here and then goes around it. So that's the idea. So we write it here and we write it here, and so this would be pressure at location 1, no, sorry, location 2, and this would be location 1. And so we can use that to calculate what the force is that's applied on this area, and that is it's equal to 30 meters a second squared, density of air, roughly a kilogram per cubic meter, area, let's make life easy, 1 meter per second squared, divided by 2, 450 newtons. If we want to work out the power, it's the force that we have to push against. You have to obviously push at this force F, and that force is going at some velocity v. It's going at 30 meters a second. So you multiply the two, you get 15 kilowatts. Actually, didn't we just get that here? It's a magic number apparently, which is probably high. I think a cyclist on the Tour de France or the Vuelta, which just finished in Spain, is about 500 watts, half a kilowatt, or maybe a kilowatt. But 15 kilowatts is high. And of course, this scales directly with the area that you chose. A meter for the front of the cowling is probably very high. So if you want to get it down to a kilowatt, which is a bit more reasonable, then you have to cut that area by a 15th. So a 15th would be that instead of being a meter wide, it would be about 6 centimeters wide. I can imagine that, right? So if you imagine the front of that cowling being a meter high by 6 centimeters, 6 centimeters is 3 inches, a bit less than 3 inches, 2.5 inches. And you could imagine that the equivalent area of that nice aerodynamic cowling was closer to that, and it would give you a number that would make sense. Okay? Same. So this is actually exactly the same as if you had a jet engine here and a truck on SFO's runway heading westwards across Oakland, I think is the particular runway it was used. Okay? Everything good? Okay. All right. Well, the other things that I was going to do today, well, yeah, let's go back to Jesse Sharp. He's our man. Do I have some space? Not much. So I will not do that. That's not what I wanted to do. I'm not very adept at this today. All right, let's do Jesse Sharp. We talked about free jets last time, and so let's do an example that looks like this. It's Niagara Falls. And so this is something like 40 meters, 120 feet. And this is our guy. So we could choose to write the expressions here at V0, V1, 2, and 3. This is all getting to be very similar, right? Remember we talked about the free jet. Free jet was convenient because in our tank for our free jet, if you remember, so actually it wouldn't be any different. Remember, it's getting thinner as it goes down. This was exactly Z. We call this Z. And because of our boundary conditions, if we wrote Bernoulli, P0, this could be 1, this could be 2, and this could be 3, just to be parallel to this. So what is this? P0 is equal to 0. Big tank approximation, V0 equals 0, and Z equals Z. So we could do the same for this. This V0 is equal to 0. P0 is equal to 0. And Z0 is equal to 40 meters, or Z. On the lip of the falls, we could imagine that V was equal to, not equal to 0, in which case that would be finite. And if we're writing Bernoulli between this point and this point, then we'd have an extra increment added to the velocity as it hits the bottom, because we'd just be adding that as part of the Bernoulli equation. But you notice that if we write it between points V0, let me write Bernoulli between those 2 points. So Z0 plus P0 over gamma plus V0 squared over 2G. And we write it at the downstream location just before it impacts, then we'd get Z3 plus P3 plus V3 squared. And so it doesn't care that we've gone round a corner. If we worked on this equation just as we did on the free jet, this would be equal to, let me call it 0. This would be Z. This would be 0 if we take our datum at this point here. Pressures are atmospheric at both these places. It makes life easy if this velocity is 0, as we've said. And the equation we get is that equation of a free jet. So that's kind of curious. This is Z, which is 40 meters, by the way. And so it really doesn't care if it's going around this bend. Bernoulli doesn't know anything. It is important that it goes around there, but we don't care about that yet because we're dealing with an approximation. Interestingly enough, if I complicate this figure by drawing Niagara Falls so that it's no longer a falls but a ramp, let's say 1-to-1, then what is the streamline velocity at V5? Well, if you write Bernoulli between 0 and 5, so if we write Bernoulli between 0 to 5, what do we get? Nothing's going to change. Everything here at point 5 is going to be exactly the same as at point 2, This is 2, by the way. Sorry. Should have shouted. Obviously the velocity here at 3 is 0, right? And it gains pressure. But if you look at the velocity at 0.5, which is equivalent to 0.2, then you're going to end up with the velocity at 0.5. You can do it. It's just equal to square root 2g h, or z. Z is the vertical distance upwards. So it doesn't care that we're going around the bend. So this would be, I suppose it would be actually be, that's the slope I'm drawing. So this would be the water that's going down the hill on this trajectory. So this would be V5. But what it would have is, if I take this part here, not doing that, I was wanting to draw a nice circle. Oh, fantastic. Is we have this going down here at 45 degrees. This would be the velocity in the streamline direction, equals v. So streamline velocity, which is always what Bernoulli is, it's always along the streamline, in direction of the streamline. This would be v5, which would be this magnitude here. This would be vx. And this would be vz. And so this is going to be 45 degrees if it's 1 to 1. This is going to be unit vector 1. This is going to be 1. This is going to be square root 2. And if we divide both sides by square root 2, this is just an easy way to get cosine and sine. Probably belaboring this. Sine and cosine of 45 degrees are just 1 over square root 2, right? Which is 0.7. So Vx is equal to Vs cosine theta equals 1 over square root 2 Vs, and Vz is equal to 1 over square root 5. So Bernoulli always gives us a streamline velocity. And we can modify that to be able to get velocities in some different directions. It doesn't care that it's gone around this corner. The vertical velocity here is the same. The streamline velocity here at 2 is the same as the streamline velocity here, but they happen to be oriented in different directions. You could argue whether they really are the same. This obviously would be less because there's friction on the bottom. We assume with Bernoulli that's inviscid, so there is no viscosity dragging it, so they are the same. And so we have to wonder about that. And so the utility of using that is that when we deal with some calculations, and so one typical fun question to do is something like this. Have a bucket sitting on a slope. Water comes out of this bucket, has an elevation attached to it. This is h. Question is, if this bucket is sitting on a plinth, which is some height d above the ground, how long does it take to, or how far does it go in its arc before it hits the ground? So, simple question. So how to solve that? Well, first of all, we want to know what the velocity at point 1 and velocity 2 is. So you could write Bernoulli between those two locations. Well, I'll write it out. z1 plus p1 over gamma plus v1 squared over 2g equals z2 plus p2 over unit weight plus v1 v2 squared. It's going to be the free jet approximation again, right? Because everything we do. Big tank approximation. So v1 equals 0. Elevation we know. Open to the atmosphere. Open to the atmosphere. Let's take the datum at this point. Well, actually we don't need to. But if we do, then this is 0. And we have this. And if you sort that out, you end up with V2 is equal to 2GZ in our thing here. Maybe I should write this as H. This is H, right? And this is 0. So we have a velocity. So what now happens to this is it comes out. So Newton says that if no force acts on this bead of water, it'll just keep on going at velocity 2 forever. Nothing to stop it. But the other thing that's going on is that gravity is acting against it. And actually, if you take this expression, I mentioned it last time, velocity is equal to 2gz. And if you look at acceleration in the z direction, we can write it as dv dt, but we can also multiply it by dz over dz. So by definition, this is velocity in the z direction. So we can write this as square root 2g. So the differential of this is square root 2g times the derivative of z with z, so it's just 2g. And the the derivative of square root 2, so this is dz of z to the half multiplied by 2g square root times z to the half. So this equation here, right? The derivative of z to the half is a half z to the minus half. So if you substitute this into this, you end up figuring out that az is equal to gravity. So this is acceleration, which you recognize as dv dt. If you multiply top and bottom just by 1, which is dz over dz, then we get a convective acceleration, which says that at this point here, as it goes down, because the bead is narrowing down, it has to be accelerating. So you take a point, you look at the velocity at that point, and how it changes as it goes down, and you look at the velocity and you multiply the two together, that gives you your acceleration, just a standard result. And so it means that the water that comes out of here is dropping at a rate of g. So you can use our expression, and so I'll just write this down rather than derive it. I'm sure you'll be happy that I do that. This is your standard dynamics equation. It says how far you go if you're going at initial velocity at time 0, and you accelerate at some amount, and you start off, I guess this is plus a constant, and if you take v equals 0 at t equals 0, then you just get rid of this constant. And so what you could do is if you're d height from here, and you start off dropping. So my vertical velocity when I come out of this horizontal tube is 0, right? So I start and I just drop. So it's the same as a ball being dropped from this location here. So I could write this expression, the vertical velocity is 0. So I can write z is equal to a half a t squared. So if I know that, then I can write that t is equal to 2 times z over g. Square root. And so I know what t is until it impacts the ground. So I could say this is 0.3. And so how far will this distance be? So this distance here is actually what I'm calling d, right? And so the distance L, velocity is equal to length over time. So length is equal to velocity times time. So the length traveled is going to be the velocity 2, which we haven't calculated, multiplied by t3. Simplest way to do it. Did I have some numbers on this? I did have some numbers. I'll just put the numbers in. So t is equal to 2 times Niagara Falls divided by 10 meters of gravity, 9.81 meters per second squared. This expression here, square root. Not feeling very mathematical today. Apparently that is square root 8, which is about 3 meters a second, which is about, 3 seconds. So it takes 3 seconds for Jesse to go across the lip and hit the deck into the plunge pool, in his particular case, in this. And so I'm just doing this as the same geometry. So this is the velocity, so at this point here, it's going at, did I do the calculation? I didn't do the calculation. No, I haven't done the calculation. So if we know the time it takes for us to go from this point to this point is 3 seconds, if we know, irrespective of the speed we're coming out of here, it's going to take us 3 seconds to get down here. And so if we know the time it takes us to hit the deck, then the distance we'll travel, if we're going in a car in this direction, traveling constantly at this free jet speed, then the distance we go is going to be just the product of velocity times time. So we can calculate that. And so that's the easiest way to show that. There's lots of permutations on that problem. I think this is a more complicated example where you have to decompose you just do the same thing. Big tank approximation, no velocity, no pressure, elevation. Atmospheric pressure, don't know what the velocity is, but we know the elevation, so we can calculate the velocity. The velocity is a streamline velocity. We can calculate the components of this streamline velocity. If it's coming out at 0.2 and going upwards at 1 meter a second, it's the same as throwing a ball up at 1 meter a second. So you can use this expression, if I can find it, this expression here to figure out where it arcs by just differentiating this expression. You can find out where the velocity is equal to 0 just by taking the derivative of this. dz dt would be the velocity. That would make this just velocity 0 plus a half a times 2 to the power t to the power 0, t to the power 1. And so you can calculate where the arc would be, and therefore you could calculate how far it goes as well. And so you can see that in other videos that we've had, and other examples that we didn't quite get to. So, yeah, ones that we didn't do. So that's it. I mean, that's about as plainly as I can take. So that kind of covers most of the things that you need in this class. You need to be able to write Bernoulli between a couple of points. You need to realize what the parameters are that define how your system is working. You need to know that the free jet, irrespective of how it's directed, it doesn't make any difference to the velocity. It's always a streamlined velocity that you're getting. It does matter what it will happen to it after it comes out of that nozzle in terms of what it will do. And I suppose you could imagine that if you had this nozzle that was pointing upwards, like this, and you wrote Bernoulli between point 1 and point 2 here, Bernoulli would tell you that by the time you get up to this point here, the velocity has to be 0. It would just be a static condition. And you can show that for yourself. But you can write that. And I guess the other key is that if you find out that you have one equation and two unknowns, then what you have to do is you have to use continuity, which basically allows you to solve two equations for your two unknowns, just by linking the two velocity terms that exist within Bernoulli. Okay, that's it. That's all I got. Questions? Applause? Not today. Okay. Fine. All right, I'll reiterate, don't forget to, if you came in late, to sign up for Monday, and today sign up for next Wednesday. A necessary evil for our class, but you should do that with the testing center. Just what we have to do. What else? First test question is almost a verbatim. Oh, it's gone very quiet. God, you're so mercenary. First test question is almost verbatim of a question that's been given in the last 8 years. I know you might not think that's a great gift, but if I say 8 years, it doesn't mean 1 year or 2 years or 3 years. Resume the chatter. That's what I'm saying. I'll leave that on the video as well. So.